So do y'all remember using the Boltzmann distribution in the fall? You know, we did it a couple of times whenever we simulated an absorption spectrum or something like that. We had to use the Boltzmann distribution to kind of see how molecules were distributed among the energy levels. And so today we're going to explore that a lot more. So it's the foundation for statistical thermodynamics. So you start with the quantized energy states. And in terms of knowing where those energy states show up, that's what you need the first semester for, right? So you have to solve the Schrodinger equation. You have to have a suitable wave function. Once you do that, then you get the quantized energy levels. And so in this spring semester, we don't go back over that. We just sort of start with these quantized energy states. And so if you're asking, well, where do these energies come from? You got to go back and get your PCHEM1 notes and say, okay, so solving the Schrodinger equation, putting in a suitable wave function, doing the second derivative, and so on. And then you get the energy values or the eigenstates for those different systems. And we're going to look at, you know, Friday and all of next week, the translational motion, rotational motion, and vibrational motion that we covered in the fall, because we know those energy equations. And so we'll look at how those energy levels are filled using the Boltzmann distribution and what kind of thermodynamic properties we get out of those. So today we're just going to focus only on the Boltzmann distribution. So it's a probability of a particle being in any given energy state, not just the ground state, but the excited states. And so this is about probability. So it's about the statistics of it all. And this is the probability equation using the Boltzmann distribution function. So you can see it in two places. You see it down here at the bottom. You see this Boltzmann distribution piece here. And in the fall, we called that B. And I guess you could call the quantum number in this case I and T. So it was a function of the quantum number and of the temperature. And then we have a particular I up here in the excited state. So this is the probability of being in quantum state I. So we have these different pieces that depend upon what quantum state you're in. And then this piece in the denominator is the normalization function, right? It's the sum of all possibilities. So this is your typical probability, the event you're interested in on top, and the sum of all the possible events on bottom. So let's look at all of these different variables. So Boltzmann's constant is K. And if you look at Boltzmann's constant, it's kind of an interesting set of units. It has joules per Kelvin. So just pause for a second and think about that. You know, we measure temperature all the time, but temperature really isn't energy. Temperature is just temperature. We'll get into how we define temperature later, but we use temperature all the time. Boltzmann's constant tells us how many joules it takes to move the temperature a certain degree. Okay, so it's sort of a natural heat capacity. So this Boltzmann constant, it takes, you know, 1.38 times 10 to the minus 23 joules to move the system 1 degree. Okay, now if the system's made up of different things, then we'll multiply this Boltzmann's constant by some scaling factor to adjust it for water or for copper or for lead. And so, but you notice that this Boltzmann constant has something to do with converting temperature to joules or joules to temperature. And so that's what it's doing here in this Boltzmann distribution function. We have Boltzmann's constant times temperature, which gives us energy. And we're taking the energy of the quantized state and comparing it to that energy that we have in the room or in the thermal system. And so it's always this ratio. How much energy do I have available because of the temperature I'm at compared to the energy of the quantum states? And it's an exponential dependence upon that ratio. And so the degeneracy of the energy levels is G. So that G sub I is the degeneracy. And that's just the count of energy levels that have the same energy. So if you have like a p orbital, there's, you know, triply degenerate. So just to remind you of a common system that you're familiar with, or like a d orbital set has degeneracy of 5. You know, an F orbital set has a degeneracy of 7. So. And then energy is this little epsilon I. So that's the energy of the quantum state. And then the temperature is T, which is in Kelvin, and it's always in Kelvin. So in these thermodynamic problems, sometimes you're given Celsius temperatures. I'm trying to be tricky. So you need to always convert them over to Kelvin, because that's the thermodynamic temperature. Okay. Now it's also very useful when we're dealing with quantized states. The energy levels can be quite close together, and a very small packet of energy would be the energy of a wave that has a few waves per centimeter, and that waves per centimeter we call wave numbers. And so it's frequent that you'll have energy spacings in wave numbers, not in joules. And so this is a good way to scale the Boltzmann distribution function. If you take the Boltzmann constant and divide by Planck's constant and the speed of light, you end up converting that joule into wave numbers, because you see the joules cancels with the joule in Planck's constant. The second in Planck's constant cancels with the second in the speed of light. And if you write the speed of light in centimeters per second, then you end up with wave numbers per Kelvin. So that's what we have here. And look how nice and neat that number is, 0.695 wave numbers per Kelvin. So that tells you in a spectroscopic system, you know, how much wave number energy you have in terms of temperature. So it's really useful if you have, like our iodine lab, the last lab you did in PChem 1, where the vibrational frequency was 214 wave numbers. And if you take 298 and multiply it by 0.695, you end up with 207 wave numbers. And so at room temperature, we have almost comparable energy available in room temperature to the vibrational excitation of iodine. And that's why we had iodine molecules in the first excited state, a lot of them. So when we did those transitions, the V double prime states where V double prime equals 0, V double prime equals 1, and V double prime equals 2, there was some in the second excited state because we had so much energy available at room temperature. And we know that we have enough energy to excite that iodine molecule because Boltzmann's constant is 0.695. You multiply that by room temperature, and you end up with something of 200 wave numbers. So you have 200 wave numbers of energy at room temperature. So that's enough to excite iodine, but it's not enough to excite like the CH stretch, which is 3000 wave numbers. So since we have a mental connection with infrared spectroscopy, we can think about the carbonyl stretch at 1500 wave numbers, the CH stretch at 3000 wave numbers. And so we know, since those are so high in frequency, room temperature is not going to be able to excite them. And we know that because we take room temperature times Boltzmann's constant, and we only have 200 wave numbers of energy. And a carbonyl stretch is 1500 wave numbers, and a CH stretch is 3000 wave numbers. So we just don't have enough room temperature energy to excite those vibrations. So that's why I like converting the Boltzmann constant over to wave numbers, because then you can compare it to things like vibrational excitation. And then also rotational constants are in wave numbers. So the rotational constant for HCl was 10 wave numbers. And at room temperature, we have 200 wave numbers of energy available. So we have a lot of spinning HCl molecules. And so that's really, again, an easy way to compare things. Now, you could take the long road and you could take those wave number values and convert them to joules, all of them. And then they would be tiny, like 10 to the minus 15 joules. And then use Boltzmann's constant, it's 10 to the minus 23 joules, and do all of those with all that scientific notation. And you're likely to screw something up because you have all these times 10 to the minuses. And so instead of converting your energy levels to joules, which is a valid way to do it, convert your Boltzmann's constant to wave numbers. And so then that makes life a lot easier. So that's the way we're going to do it today. We have a couple of problems that we're going to work in wave numbers. And so you can just use this version of the Boltzmann constant. So let's talk about this partition function. That denominator in the probability distribution function is called the partition function. And that is something that you hear that word, you know you're in statistical thermodynamics. That's like the governing calculation for all of statistical thermo. And so this is given the variable Q, and this is the way it's typically written. A lot of times they use beta here. And so this looks different than the previous page, but beta is just 1 over KT. And so that's, I couldn't get her to do it, but I always wanted to make a ball cap for my daughter that had beta to -1 on the front because her name was Katie. And she was like, no. So anyway, she is a math major, but that was too far. So beta to -1 is KT, or beta is 1 over KT. And it's just, I put that in there, not because we necessarily need to use it, but that you'll see that in the book sometimes, that the partition function is e to the minus beta epsilon. And you're like, wait a second, where'd beta come from? So it's just epsilon over KT. And so then the probability of any particular configuration is this Boltzmann factor for that particular level on top, and then Q on bottom. So in order to calculate the probability, you have to sum over all of the states first. So we have to do that sum first to get the probability, to get the partition function. Now this partition function is what it says. It's calculating the sum of all of the places where molecules are. So molecules are partitioned into energy levels. And this is telling us sort of how many partitions we have, how many energy levels are populated at a given temperature. So it's a normalization constant for this probability distribution, but it is also a sort of a measure of how excited the molecule is. So if you are all in the ground state, essentially, if we set the ground state energy equal to 0, we have e to the 0. So the lowest number for the partition function is 1, because everything's in the single partition, everything's in the ground state. And then it goes up to infinity from there. So as we raise the temperature, we excite all of the molecules in the system. And so there's essentially all of these quantum systems were unbound on the top. The energy levels could just go up to infinity. And so at a high temperature, an infinite temperature, then this partition function can go to infinity. And so these are some features of the Boltzmann distribution law. So if you look at your handout, there's some missing words on here for sure. So we talk about microstates, and those are particular ways to build the system. And so if I had numbers on my molecules, this would be the particular position of molecule 1 and molecule 2. And so a microstate would be, say, molecule 1 in the ground state, molecule 2 in the excited state. And then the other microstate would be 1 in the excited state and 2 in the ground state, or both in the ground state or both in the excited state. So how you have your little numbered molecules is a microstate. The configurations are, if you delete the numbers and just look at whether you have molecules that are excited or not, regardless if it's molecule 1 or molecule 2. And so if you'll notice that in my little example, let me just draw these 4 systems. So I can have 1 and 2. I can have 2 and 1. I can have 1 and 2. Or I could have 1 and 2. So these are 4 microstates for 2 molecules and 2 energy levels. And notice this one can be arranged. Essentially, it's the same one. If I delete the numbers on the molecules, this is a particular configuration. So configuration 1, configuration 2, configuration 3. This one's the most probable because there's 2 ways to build it. And so that's what we mean by the dominant configuration of microstates, is the configuration with the highest probability. So there's two events there. There's two ways to build that one if we ignore the numbers. And so that's going to be the one that's most probable. So when we calculate the probabilities, it will have twice the probability of either one of the other two. Now, the adjacent configurations of microstates are insignificantly different from the dominant configuration. And let's just think about a larger system like 50 coin flips. If we were to plot the 50 coin flips, I'll say number of tails. Let's see, how do I want to do this? The frequency. Now this is the number of tails here. And this is the frequency. So how often you get that? And so right here at 50 coin flips, this would be 25. Because there's a 50-50 chance of getting heads or tails. But this is saying that there's an insignificant difference really between getting 24, which would be right here, and getting 26, which would be right there. So you see the equilibrium or the average or the adjacent configurations of microstates, or the probabilities of those is almost identical to the one that's right at the most probable. But it does fall off. If you get pretty far away from 25 tails, then you see that the frequency of getting that result really drops off. And then the area under this curve is equal to 1. So those would be our normalized probabilities. Now we have observations of the macroscopic system will be governed by the dominant configuration, and so it will appear unchanging. So if we had a system that was essentially like this tail flipping system, and quarters were flipping back and forth and so on, and we were able to monitor that over time, it wouldn't appear to change at all. But we might have a one with 26 tails flipping to 24 tails, and one with 24 tails flipping to 26. And they would be exchanging places. So these configurations might have different quarters in them, but they would have the same, from our detection, they would look identical. And so this distribution would be stable. And that's actually what's happening when we're looking at a system at equilibrium. Your reactants are turning into products and your products are turning into reactants, but the concentrations of those look the same because we don't have labels on our molecules. And so that's an important sort of statistical support for this idea of equilibrium. And you know that equilibrium is defined as the forward reaction rate has now become equal to the reverse reaction rate. So molecules are being made into products and being destroyed or reverted back into reactants at the equal rates at equilibrium. And you don't see anything happening. You could take a sample and measure it and you get a certain concentration, and the molecules removed from reactants and products, you go test, and there's others that are being made into reactants and products at the same time. And so you just don't see much of a change in this distribution, even though a lot is happening inside of nature. We'll calculate when we get to the kinetic theory of gases how fast these molecules are moving. They're colliding like 10 to the 13 collisions per second. You can think about that. A billion is 10 to the 9. So a billion collisions per second is way past that. 10 to the 12th would be a trillion. Is that right? Yeah, a trillion collisions per second. So this is 10 trillion collisions per second in a gas. So that's argon. So that's amazing how fast these molecules are banging into each other. So they're converting to reactants and products incredibly fast. Those atoms can move around and molecules can be made and broken to bits in almost, well, what we would say no time at all. 1/10 trillionth of a second. And so this apparently unchanging dominant configuration is what we mean by the equilibrium state. And because it's described by the Boltzmann distribution law, if it's a Boltzmann distribution, it's at equilibrium. They are synonymous. And so we use this Boltzmann distribution law to determine if something is at equilibrium. Now we can tell, like spectroscopically and so on, if the system appears unchanging. But if we actually get down into the energy levels and the population of the energy levels, if it matches the Boltzmann distribution law, by definition, it's at equilibrium. It's at thermal equilibrium. Okay, so let's get into some of the problems. So this is a typical two-level problem. So this is a classic, so like on the GRE type problem. Is you got a classic two-level system. So what are the population probabilities of a two-state system with an energy spacing of 200 wave numbers at room temperature? And so you should have a blank sheet of paper down below where you can do the work. I'm just going to build this table. You have the table up top. So I'm just going to show you where all these numbers come from, okay? And so I like to start out with sort of the energy level index. So we give these quantum states like 1 and, or we'll say 0 and 1, 0 and 1. So state 0, state 1. We have the energies from our two-level system. So that's going to be an energy of 0 wave numbers and 200. And then let's go ahead and write out the degeneracies for these. So we're looking at these are each 1, but they don't have to be. In the next problem that we do, there'll be some degeneracy. We'll see the effects of that. And so then let's calculate the Boltzmann distribution piece. And here we'll have to get a calculator out. I know you have the answers right up top, but that's really just to check your work. So let's go ahead and do the calculation, just so you know how to bust it through your calculator. Now this first one's really easy. I'll wait for you to get your calculator. So in this first situation, we have e to the minus 0 over kt. So that one is easy to do, right? It's e to the 0. So that's equal to 1. Then we have e to the minus 200. And we've gone ahead and calculated what kt is at room temperature. It's 207. Okay, so that's really essentially 200 over 200. So that's e to the minus 1. I did this just to make it easy for us. So we have 1, change the sign, and then we have the exponential function. So 0.37. Is that right? Yeah. Okay. Did you type in the 207?
Yeah, I put e to the minus 200 over 207.
Yeah, I just simplified it to 200.
Oh, yeah.
Yeah. So, but if you want, yeah, that's either way is great. Yeah. And so then we have this, this Q is the sum of these Boltzmann pieces times the degeneracies. And so it's these two here, this sum product of 1 times 1 and 1 times 0.37. So that's Q is equal to 1 plus 0.37 is equal to 1.37. So that's our partition function. And that's telling us that we have some excitation in this system. Because if it was all in the ground state, then it would be 1. And if it was all in the ground state, this piece would be 0. Okay. So, yeah. And so how would we get 0? Well, we'd get 0 if, let's say our temperature was so low that this number was essentially e to the minus infinity. So e to the minus infinity is essentially 0. And so then we would have no excitation. Okay, so then the next piece is going to be the probability piece. And so this is going to be this, see, look here, it's the individual Boltzmann factor divided by Q. So it's this GI times BI up here. So it's this row. So essentially 1 divided by 1.37. And so it's 0.73. And then the next one is 0.37 divided by 1.37. So when you do it in a table format, it's really easy. And this should be 20, this should, 73, yeah, this should be, yeah, 27. And so there may be some slight differences from the answers I have on this page. See, yeah, 3.8 and so on. But, you know, and if I were grading this, it'd be insignificant. You know, if I saw that you assumed it was 200 versus 207, that's fine. You know, you're showing me that you know how to do the problem. And so these are our probabilities. It's always good to check your work. And so let's add those up. They should equal 1. Okay. And so that's good. And so what we have here, now let's look at what this means. These are what the numbers are. It's always good to ask, what does this mean? So this is the probability of being in the ground state. So there's 0.73 molecules in the ground state and 0.27 molecules in the upper state. So if you had 100 molecules, you'd have 73 in the ground state and 27 in the excited state. And it's temperature dependent. And it's dependent upon the degeneracy of the energy levels. And it's dependent upon the number of energy levels. So we have a 2-level system. If we had added a 3rd level, that would change our partition function. And because it changes the partition function, it changes the denominator of all of the probabilities. And so all of the probabilities change. So, you know, if you change the partition function by adding energy levels or splitting them in 2 and something like that, you're going to change the populations. And essentially this, I like to think of this is like a musical chairs. And if you split some chairs in 2, now we have 2 chairs, and it changes the system, it changes the game. So let's look at a change, a typical change. Well, here's the numbers that we just calculated. So that's good to check your work. Let's split that upper level. So what are the population probabilities of a 2-state system with an energy spacing of 200 wave numbers at room temperature with a doubly degenerate excited state? So let's quickly do our table here. We have our indices with 0 and 1. Epsilon was 0 and 200. The degeneracies were 1 and 2 for the excited state. So that's the only change in the table right there, is that 2. Let's see, e to the minus epsilon over KT. You know, this one doesn't change because the ground state is still energy of 0. And so e to the 0 is 1. And then the next one doesn't change, it's still 0.37. But look at our partition function now. We have 2 times 0.37. And so Q is equal to the sum of all of those. I'm just going to add them together instead of writing out the equation. 1 plus 2 times 0.37. Okay, does somebody already have that for me? Louder, please.
1.74.
1.74, okay. Notice it's larger, so we have more excitation. Okay, so let's calculate our probabilities. 1 over 1.74. What's that one?
0.57.
0.5. Okay, and then this one is going to be the 0.74 over 1.74. So two-level systems are really easy. So this should be a 43, right?
Yeah, it's 0.425.
Yeah. And so we do our check, and that should equal 1. Good. And then so now we can look and see what this means. So we have 57% chance of being in the ground state. This whole thing up here is 0.43. So it'd be 21.5 for each one. So that's the individual probabilities of being in all of those energy states. There's a 43% chance of being excited. But if you're looking at the, whether the molecule's on the left side or the right side, it's 21.5% chance of either one. So that was, again, we could focus on the calculations, pretty easy calculation for a two-level system. But let's think about what this means. This is a pretty interesting result. So I want you guys, since it's such a small group, compare our previous calculation to this one. What's the only thing that changed? The degeneracy. Now, the probabilities changed too. Now the only input that changed was the degeneracy. What was the output? We calculated the probabilities. They changed as well. What happened by changing the degeneracy? Put it in your own words. More molecules went into the excited state. Did the temperature change? Isn't that weird? I want you to struggle with that.
So is that why iodine worked at a lower phase because it had more states that it had more degeneracy, so they were able to do it higher than say like a CH stretch?
No, because there wasn't any degeneracy in the vibrational levels, but we did have a third level, a fourth level, and a fifth level. So that's why those third and fourth levels were populated, because they were there. Then we have degeneracy. So now we have another chair. And if you're playing musical chairs, they're going to sit there. But it's so weird to think about. All you did was make a degenerate energy level in the excited state, and you have more excitation, but you don't have a different temperature. That's weird, isn't it? I just think that's weird. And that just sort of shows the statistical nature or behavior of molecules. This is what happens in statistical thermodynamics. If there's energy levels there, and if there's molecules, some molecules are going to have enough temperature to go get into that spot. They'll do it. They'll populate all the available energy levels. Okay. What's interesting too is in this system, the average energy is higher, but the temperature is the same. And so that's another thing that's weird. There's something about the system, about the molecules that make up this system that allow them to store more energy at the same temperature. And so that's when we talk about heat capacity. So this molecule with a degenerate excited state has more heat capacity. You can put more heat into it, more energy into it at a given temperature. And so we will learn more about that as we go on and we get to bulk properties. Let's try to do this next problem in the last 5 minutes or 10 minutes we have here. So here are your answers just to check your work. This is an interesting one. What temperature in this system would yield a 50% population probability for the ground state? And so we're asked to now go backwards. All right, we start with the probabilities and we go backwards to get the temperature. And this is also a classic two-level system. And so how could we figure this out? Well, let's take that probability equation and see what we have here. We have the GI e to the minus EI over KT in the top part over Q. And we have all of these variables except for T. So we should be able to solve for T. So let's go ahead and put everything in that we know. We know that the probability is 0.5. We know that the, let's see, 50% probability for the ground state. So we're talking about the ground state. So we have,
You know, the ground state will always be 1, so we can.
yeah.
For the top, we can set for the higher energy level 200 because we know that one gives 1, and then the bottom would be 1 plus the numerator.
Yeah. So we can, I'll go ahead and write out all the pieces for now, but then you might be able to simplify things. And so the degeneracy of the ground state is 1, e to the minus 0 over kt. Okay. And then on the lower state, we have a degeneracy of 1. This is, I'm going to write out the sum. Plus the degeneracy of 2 here, e to the minus 200 over kt. All right. So we can't assume that kt is 200 because that's room temperature and we're trying to solve for the temperature. All right. And so we know these are e to the zeros no matter what the temperature. So this piece right here is 1. We know this piece is 1. And so the only piece that we have left is this with the temperature in the bottom. So we can clean this up. Okay. And so we end up with, it does get kind of ugly. We're going to multiply this whole thing, bring the denominator over 0.5 times 1 plus 2e to the minus 200 over kt is equal to 1. We'll multiply this 0.5 through. 0.5 times 2 is 1. So we'll just have this e to the minus 200. If you say, hey, you know, you can stop me at any time and say, whoa, hold on. Okay. And so then we'll subtract this 0.5 from both sides. And then now how will we get rid of the exponent?
Natural log.
Yeah, so we take natural log of both sides. All right, so we end up with minus 200 over kt is equal to the natural log of 0.5. And so then now we can move things around. Let's start back over here. We'll have temperature. So I've moved temperature over to the right. I'm going to move the natural log over to the left. So we have a minus 200 over k ln 0.5. Okay. And this was wave numbers. I need to use my units. Sorry. Wave numbers. All right, so what is the natural log of 0.5?
0.693147.
Okay, so it's equal to 200. And then the Boltzmann's constant was 0.695 wave numbers per Kelvin. And that's good because that Kelvin's going to come up on top. And then the natural log of 0.5 is unitless. And so what was it again?
0.693.
Weird. Because it's so similar to the Boltzmann constant. Okay, why do we have a negative sign?
What's a negative 0.693?
Okay, very
Oh,
good.
yeah.
Good.
Sorry.
So there's, okay.
It
So, but did notice how, yeah.
Stop using them.
Yeah, you notice how the negative temperature rang an alarm bell in my head. It should yours too. So, very good. So what do we end up with in terms of temperature?
415 Kelvin.
415 Kelvin. Okay. Does that make sense now? So why do you say it makes sense?
It's above temperature, right?
So what was our experience with the previous two calculations?
You're at temperature.
They were at room temperature, and what was the population of the ground state?
It was always
Higher than 50%, yeah. So as we raise the temperature to 415, eventually we get to where it's a 50% chance in the ground state and a 50% chance in the excited state, which is 25 in each of the two ones. So
It's an exponential function, right?
yeah, so you got to really crank up the temperature to get those molecules to move to the excited state. So it does make sense there would be a higher temperature. So there's two things that you want to check. You wanted to say, like I noticed there was a negative temperature coming out because I didn't have the negative on the log of 0.5. And so that's one check that's real easy. It's like, oh, I got negative temperatures. Okay, the other thing you want to check is, does it make sense? You know, if we got something like a 5 Kelvin, you know, then there'd be a problem because it's telling us at 5 Kelvin, I have a 50% chance of being excited or in the ground state. But I did on other problems, whereas at room temperature, I had 73% chance of being in the ground state. So there was something wrong with my math. I must have, you know, made a mistake somewhere. So it's always good because PChem problems are difficult in that respect. You have to sort of not just do the problems to do the math, but do the problems to get insight into nature. And that's really what we're trying to develop. We're trying to develop both. And you've got some math skills you've demonstrated in calculus 1 and 2, but I also want you to connect that calculus to nature and think about, does this make sense? The does this make sense question is, how does this describe nature? And does that fit with reality or not? So that's amazing. We hit the target just right on time. That's where I wanted to get today. So.